So now let's check what are symmetric and skew symmetric matrices. So first matrix which we are going to see is the symmetric matrix. So for a matrix to be symmetric, what has to be the condition means A complement has to be equal to A. So this is the condition for a matrix to be symmetric, right? So the complements have to be equal, then only they are symmetric, right? So let's assume we are having a matrix A such that it has the element 6 4 4 0 like this, and now we are taking the like transpose, right? A complement or A transpose. Now we'll do, right? Now just first row becomes the first column. So if you check 6 4, right? Now second row becomes the second column. So 4 0 elements are replaced here. So if you compare A complement and A, both have every element same. 6 first element, 4 is the second element, third element is also 4, and fourth element is 0. So both are equal. So this matrix actually is a symmetric matrix, right? As both are equal, both are symmetric. And for symmetric matrices, it has to be a square matrix. Only a square matrix can be symmetric. So a rectangular matrix, it cannot be symmetric if this is having a 2 by 2 order, right? So the number of rows and number of columns have to be equal, then only we can check if they are symmetric or not, right? So if the number of rows and columns are not same, then the order will be reversed and they will not be symmetric, right? So all rectangular matrices, they are not symmetric, right? Now let's check what is a skew symmetric matrix. It's very similar to the symmetric matrix, just the only difference is A complement or A transpose, it will be equal to negative of the initial matrix A, right? So minus A. So for example, let's take a matrix B such that it is equal to 0 3 minus 3 0. So here also it has to be a square matrix, then only we can check if it is skew symmetric or not, right? So now let's check what is B transpose or B dash. So the first row becomes the first column, right? So 0 and 3, and now second row becomes the second column, minus 3 and 0. So if you compare both the matrices, right, B and B complement, instead of 0 we are having 0, instead of 3 we are having minus 3, and instead of minus 3 we are having 3, and instead of 0 we are having 0. So if you check both the matrices, they are having the same elements, just the sign is opposite in each case, right? So B is equal to negative B complement. If you take the negative of B complement, right, what it would be? 0 times minus 1 would be 0, and minus 1 times minus 3 would be plus 3, and 3 times minus 1 would be minus 3, and 0 times minus 1 would be 0. So negative B complement, it's actually equal to B, right? So when that is the case, we say the matrix B to be skew symmetric, right? And we can also check skew symmetric only if it is a square matrix. And one more condition is there for a skew symmetric matrix: all the elements of the diagonal, it is 0, right? The diagonal elements, they have to be 0, then only it will be a skew symmetric matrix. And also A complement should be equal to minus A, right? So both these conditions should be satisfied, then only we can check if it is skew symmetric or not. So now we'll be proving a theorem here. So A plus A complement, it is a symmetric matrix, right? So for that I have given you an example here. So this is the A matrix given here. So let's do A plus A complement and let's check if it is symmetric or not, right? So what is our A? Write it down first, 5 7 8 1. Now our A complement is just the reverse of this. First row becomes the first column, So 5 and 7, and second row becomes the second column, right? 8 and 1. Now you have to just add both of them and check if they are symmetric or not, right? And 5 plus 5 would be 10, 8 plus 7 would be 15, and 8 plus 7 would be 15, and finally 1 plus 1 is 2, right? So let this matrix be the P matrix. Okay, this is our P matrix. Now checking the P dash, right? That is the transpose of this matrix. So first row becomes the first column, and second row becomes the second column. So if you check, both these matrices are equal, right? Even after taking the complement, right? This means that this is a symmetric matrix, and hence we have proved that A plus A complement or A plus A dash, it is equal to a symmetric matrix, right? And now we have to also prove that A minus A dash, it is the skew symmetric matrix. So for that, just taking the same matrix A, right, and now doing the subtraction, right? Now what is our A complement? We already found out before. And now just do the subtraction. So 5 minus 5 would be 0, 7 minus 8 would be minus 1, and 8 minus 7 would be plus 1, and 1 minus 1 would be 0, which is our Q. Okay, let's assume this to be the Q matrix. Now let's take the Q dash, that is the transpose of this matrix, right? So first row becomes the first column, right? 0 minus 1, and second row becomes the second column, 1 and 0. So if you compare Q and Q dash, instead of 0 we have 0, instead of 1 minus 1, and instead of plus 1 we have minus 1, and instead of 0 we have 0. So every elements are having just the opposite sign. If you check, that is Q is equal to negative Q dash. So when this is the case, we say it to be a skew symmetric matrix, right? So that's why A minus A dash is a skew symmetric matrix. We have just proved that, right? And also one more thing we have seen here, just when we are doing the subtraction, right, difference, so what happens means, if you check the diagonal elements, they became 0, right? So that is another case for skew symmetry. So this is the condition: A minus A dash is a skew symmetric matrix, and A plus A dash is a symmetric matrix. So now we'll be proving one more theorem here. Any matrix, it can be represented as the sum of a symmetric matrix and the skew symmetric matrix. So this is the condition how it should be represented, right? So A is equal to half times A plus A dash plus half into A minus A dash. So I have taken the same matrix which we did before for A plus A dash and A minus A dash, so it would be easier, right? We already did every step before. So this is our A, and this is A plus A dash we found out before, and this is A minus A dash we found out before. And we know that A plus A dash was symmetric, we found out, right? And A minus A dash was skew symmetric, that also we found out before. Now just let's substitute and check if this theorem holds or not, right? So we have half, right, times the element 10, 15, 15, 2 plus half our second matrix, right, this one, 0, minus 1, 1 and 0. Now just multiply this half inside, so it would be 10 by 2 would be 5, 15 by 2, right, 15 by 2, this is also 15 by 2, and 2 by 2 would be 1, plus 0 by 2 would be 0, minus 1 by 2, 1 by 2, and 0 by 2 would be 0. Now we have to just add both of them and check what's the answer. 5 plus 0 would be 5, 15 minus 15 by 2 minus 1 by 2, right? So it will be 15 by 2 minus 1 by 2, and this is 15 by 2 plus 1 by 2, 15 by 2 plus 1 by 2, and 1 plus 0, so 1, right? Now let's simplify. 5, 15 minus 1 is 14, and 14 by 2 is 7. Then 15 plus 1 is 16, and 16 by 2 is 8, and finally 1. So this is the answer, right? So this part, the right hand side, we already did, and we got this as the answer. So now if you check this with the left hand side, A matrix. So what's our A matrix? If you compare these two matrices, right, both are equal, right? This is equal to this. So this proves the theorem that A can be represented as the sum of a symmetric and a skew symmetric matrix, right?